Okay, so we'll continue with our development of hyperelastic strain energy functions. And at the end of the last segment, we concluded that the requirement of objectivity or frame invariance okay, and this requirement implies that psi, strain energy function, which we think of as a function of f, can only be written as a function of f through u, the stretch tensor, or equivalently, once we have that, we have the others, right? The other tensors which are also obtained from u. What I want to do in this segment is talk about a few examples. Okay, so example 1 is what is probably the easiest form of a hyperelastic strain energy function for nonlinear elasticity. Okay, so the first example is what we will what is called the Savinon-Kirchhoff model. Okay. Okay. So this is written in terms of two material properties, right? And it depends upon two material properties which are denoted, which are called the Lamé parameters. Lambda and mu. All right. Of these, lambda, both these parameters can be rewritten in terms of elastic constants that are more familiar from the study of linear elasticity, right? Elasticity with small strains. Okay. So lambda can be written in terms of the and those two parameters from linear elasticity are the Young's modulus and Poisson ratio. Okay, so in terms of those two parameters, lambda can be written as nu e divided by 1 plus nu times 1 minus 2 nu, and mu is e, which is the Young's modulus, over 2 times 1 plus nu. Okay, where here we have E is the Young's modulus, and nu is the Poisson ratio. All right. Okay, so in terms of these two parameters, the way we write out our strain energy function is by using the parametrization in terms of the Lagrange strain E. All right, and this is psi bar is 1/2 lambda times trace of E the whole square plus 1/2 times 2 mu times E contracted with itself. All right. Okay. I ought to mention that the fact that we have a strain energy function depending only on two parameters is related to the other fact that the kinds of strain energy functions we are going to look at right now, the remaining ones that we look at today, are all for isotropic materials. Okay? And I use that term recognizing very painfully that we haven't yet talked about isotropy and what that means. That is another discussion we will get to in a few more segments. Okay? So I should mention that, I should probably mention right up here, okay, that this is for isotropic materials. I also will make the comment that if you look at this strain energy function as we've written here, right, this one, and you compare it with the strain energy function for isotropic linear elasticity at small strains, you will find that the form is very similar. It's in fact pretty much the same form for isotropic materials, except that instead of the small strain tensor, we have the nonlinear strain here, E. Okay? Just a comment, right? And it is in this sense that the Samanon-Kirchhoff model is the simplest of the nonlinear elasticity functions. Okay? Also for that reason, it's the worst, right? It's the poorest model of nonlinear elasticity we have. Okay, which satisfies all the requirements, but still is not a very good representation of all the nonlinearity that actually exists in materials. All right? And of course, this thing by construction satisfies objectivity. All right? One thing we should note is that, and I'll probably just state it here, is that it satisfies frame invariance because it depends upon E. It's parameterized by E. Okay, frame invariance or objectivity. Now this requirement of objectivity and frame invariance on the strain energy function is fundamental. Okay, all right. This is a fundamental requirement. Okay, and very simply put, a strain energy function that does not satisfy this requirement is really not worth any effort, right? It's fundamentally wrong, right? Because it will have this property that under rigid motions you will be storing energy in it. Okay, all right. Okay, so this is what we have for the Samanon-Kirchhoff model. What one can do from here is the following. One can go ahead and compute the stresses. So the stresses that one can compute, okay, are the following, right? Now, we know that we have a hyperelastic material, all right? And you remember for a hyperelastic material, the requirement is that P, the first Euler-Kirchhoff stress tensor, is the derivative of our strain energy density function, right, with respect to F. All right? Now, it is a not terribly difficult manipulation to show that you could, well, okay, the first thing we can show is that once we have this form, we can also write this as a derivative of maybe E, but then we would be using this form of the strain energy function, right? Psi hat, which depends upon E, contracted with the derivative of E with respect to F. Okay? Right? And this is because when we think of the strain energy density function, we know that there are a number of parametrizations for it. We've just demonstrated that. And we could write the parameters, we can in particular pick the parametrization that we just put down. Okay? All right. So we have this relation. And from here, once we have this expression for P, we could go ahead and compute the other stresses. Okay? In particular, we have S, which is F inverse of P. Okay? And if we go through this motion and compute and use this result from the first line, what we will be able to see is that this works out to F inverse partial of psi hat with respect to E contracted with partial of E with respect to F. Right? And just to make clear how things are working here, let's do that. Okay. Furthermore, when you carry this calculation through, what you will see is that this essentially reduces to the partial of psi hat with respect to E. Okay? It's worth doing this little calculation, so let's go ahead and carry it out using coordinate notation. Right? So, in coordinate notation, this formula, okay, this formula turns out to be, so in coordinate notation, okay, in coordinate notation, what we will see is that we have Sij equals F inverse. Let me leave this with indices capital I, little I, and here I need to have indices. Okay, I'm going to carry out this derivative with respect to E indices. I'm going to introduce new indices there, KL. The contraction works out to be derivative of E KL with respect to now F has to have indices little I, capital J, okay, for everything to work out. Okay, and if you look at how the indices are being contracted out, you will see that indeed on the right hand side we have free indices capital I, capital J. All right, now all of this is very clear, except let us it is this term that we need to work out. Okay, so let's do that. Now remember that if we have EKL, we have that is being 1/2. Now it's 1/2 C minus the isotropic tensor. Okay, and C is F transpose F. Okay, so we will write F transpose as F little j capital K, F little j capital L minus delta KL. Okay? All right, so we will now go ahead and do that derivative. Okay, so with that we see that derivative of EKL with respect to F little I capital J equals derivative with respect to F little I capital J of 1/2 F JK F JL minus delta KL. Okay? It's not difficult to calculate because very nicely we get this, we apply the product rule, and remember that these sorts of derivatives throw up for us the Kronecker delta. Okay? So when we apply it to the first term in that product of components of F, and that should give us delta J I delta K J F little j L. Okay, and of course the derivative of the Kronecker delta, delta KL with respect to Fij is 0. Okay, so we ignore that term, right? And the next term we get will be Fjk coming along for the ride, and the derivative applied now to Fjl. Okay, and likewise that will give us delta ji, delta lj. Okay, the Kronecker delta then does its work and leaves us with f delta kj f little I L plus delta lj f little I k. All right? Okay. So, what this implies then is that Sij, which we said was F inverse capital I little I derivative of psi hat with respect to E KL, and then we had this derivative of, we had that term, right? And we now know what that term works out to. So we have 1/2 delta kj FIL plus delta LJ FIK. Okay, we're pretty much there now. All we need to do is very calmly let the Kronecker delta do its job. Okay, so we have F inverse I little I. Okay, now we come to the next term, right? What I'm going to do is break it up into two terms. I'm going to pull out the half here. Okay, in the first case, the delta kj does its job and it acts upon that component, right? That index, and converts the derivative here to partial of psi hat with respect to E JL. Okay, and we have F I L. Okay, and for the next term we have 1/2 F inverse capital I little I, and now the L from the Kronecker delta acts upon that L. Okay, and so we get a derivative of psi hat with respect to E. Let me see now what happens there. You get a kj f I k. All right. Okay, and now we see that very conveniently in both cases we have an F inverse F, and likewise here we have an F inverse F. Okay, so what happens there is that we just get two more Kronecker deltas. So out of this term we get delta IL partial of psi hat with respect to E JL plus, for the second term we get 1/2 delta IK partial of psi hat with respect to E KJ. And now we're done. All we need to observe is that once again the Kronecker delta is going to do its work. It's going to convert that L index on the derivative to an I, and here it's going to convert that K index to an I. Okay, so what we arrive at then is that Sij equals 1/2 partial of psi hat with respect to E. Let me see, do I get an Ij or a Ji for the first one? I get a Ji. Ji plus 1/2 partial of psi hat with respect to E Ij. Okay, but now E is symmetric, right? So we see that this basically is partial of psi hat with respect to E ij. Right? We could have turned it around to ji. It doesn't matter because S is symmetric as well. Okay. All right. So we've demonstrated that. Now, if you apply this result to our formula for the form that we have for our strain energy function, 1/2 lambda, what is it, trace of E square plus 1/2 times 2 mu times E contracted with E, right? You apply this general result for S to this particular strain energy function. What you will see is that you get, so what this implies then is that S equals lambda trace E. Okay, it's a scalar, isotropic tensor plus 2 mu E. Okay, so we have this nice simple result for the second Piola-Kirchhoff stress. Okay, it's symmetric, and it's symmetric because, of course, the first order isotropic tensor is symmetric and E itself is symmetric, so we do indeed get that S is symmetric. Okay, so we see, of course, that S equals S transpose. Okay. Now, when you look at this, you will see that we have, for the second Piola-Kirchhoff stress, a formula that is linear in E. Okay? So you may wonder, have we somehow collapsed back to linear elasticity because the stress-strain relation seems linear? Well, yes, the stress-strain relation is linear, but remember, the strain itself is nonlinear, right? Because the strain involves, it's F transpose F, right? Okay? So relation between S and E for this particular model is linear, but E, which is 1/2 F transpose F minus the isotropic tensor, itself is nonlinear in the displacement gradient, right? That term itself is non-linear in F, where F itself is isotropic tensor plus derivative of the displacement with respect to position, right? So what we're seeing is that it is non-linear in that term. Okay, so this is how we see nonlinear elasticity still at work here.